Hi everybody, today we're going to go over written exam for Module 3. My name is Alyssa Pierce. Okay, so let's just dive in. So we see that for number 1, we are to use the divisibility test to decide which of the numbers 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 is a divisor for all the numbers in the left column of the following table, which is down below. The number 684 was done for us. We are to explain the divisibility for numbers 2, 4, 5, 6, and 10, and then show our work to apply divisibility rules for 3, 7, 9, and 11. So write yes or first for each number and then follow with the explanation of work. Okay, so for the numbers 3, 7, 9, and 11 were to show our work. The table didn't leave me enough room, so those are down below. So we'll walk through those. But first, we're going to go over 2, 4, 5, 6, and 10. So I'm going to go over the divisibility rules, which are found in my 5 sentences. So to solve this problem, we must first know what the divisibility tests are. Some divisibility tests are easier to remember than others. For 2, the last digit must be an even number, 0, 2, 4, 6, or 8. For 3, the sum of the digits must be divisible by 3. For 4, the last 2 digits must form a number divisible by 4. For 5, the last number must be 0 or 5. For 6, the number must be divisible by both 2 and 3, since 2 times 3 equals 6. For 8, the last 3 digits have to form a number divisible by 8. For 9, the sum of the digits must be divisible by 9. For 10, the last digit must be 0. For 11, you have to take the alternating sum of the digits in the number read from left to right. If the number is divisible by 11, then so is the original. So what that means is if we had 2,728, you would say 2 minus 7 plus 2 minus 8 equals negative 11, which we know is divisible by 11. So once you know these rules, you can apply each one and fill out the table above. So let's go back up, and we were asked to just show 2, 4, 5, 6, and 10 on the table. So for the first number, let's get, there we go. Yes, because the number ends in 4. This one, yes, because the number ends in an even digit, 4. No, because this number ends in an odd digit. Yes, because this number ends in 0. Yes, because this number ends in 0. And yes, because this ends in an even number as well. So for 2, we have, we take the last 2 digits. If those are divisible by 4, then so is the whole number. 84 divided by 4 is 21, so yes. 64 divided by 4 is 16, so yes. 51 divided by 4 is 12.75, so no. Here we have 90 divided by 4 is 22.5, so no. Yes, because 40 divided by 4 is 10. Yes, because 28 divided by 4 is 7. So for 5, we just look at the ending number. If it's not 5 or 0, it's no. So no, because this number ends in 4. No, the number ends in 4. No, the number ends in 1. Yes, because this ends in 0. Yes, because this ends in 0. And no, because this ends in 8. For 6, we have the divisibility rule. If it's divisible by 2 and 3, then it's divisible by 6. So we just have to look at my above chart number. So yes, because that's divisible by 2 and 3. Yes, because that's divisible by 2 and 3. No, because while it's divisible by 3, it's not divisible by 2. Yes, because this number is divisible by 2 and 3. No, because it's not divisible by 3. And yes, because it's divisible by both. So then we're going to go down to 10. 10 is pretty simple. If it doesn't end in 0, then obviously it is not divisible by 10. So we have no for the first 3 numbers, yes for the next 2, and no for the last. So we're going to go down to the ones that I had to show my work on, because while I put some of it in the box, most of it's hard to read. So we're going to just scroll down to those. So we have for 3, I've written out each number. Now the rule for 3 is that you add all the digits, and if that number is divisible by 3, then so is the whole number. So we have yes for this one, yes for the next one. Yes, because you'll just see that I've written out the number 5 plus 1 plus 0 plus 5 plus 1 is 12. We know that's divisible by 3. So we just keep going through all of those, and that's how we do divisibility by 3. Now, divisibility by 4 is pretty cool. I've written the whole number, and then I've just underlined the last 2 digits of the said number to see if those are divisible by 4, because that's how you count that. So 84 is the last 2 of this number. So we have 84 divided by 4 is 21, so yes. 64 divided by 4 is 16, yes. 51 divided by 4 is 12.75, so no. And so on. So for 7, the rule is that you take the last digit of the number double it, and then you take that number and subtract it by the numbers that you didn't use before. So for example, we have 684. 4 doubled is 8. I have that written out. And then we take 68 minus 8 is 60. 60 divided by 7 is 8.57. So no. So let's go down to one that's yes, so you can see. So we have the 51,051. So 1 doubled is 2. 51,005 minus 2 is 51,003. That divided by 7 is 729. So that's a yes. And you just keep doing that throughout. So for 8, what we do is we take the last 3 digits of the number, and if those are divisible by 8, so is the whole number. So 684, that's all 3 digits. So is that divisible by 8? No, because you come out with 85.5. But for 2064, we all know that 64 is divisible by 8, so that is a yes. You just keep going through like that. Now for 9, it's much similar to 3. You just add all the digits together. If that number is divisible by 9, then so is the whole number. So for the first one, 684, all those added together is 18. 18 divided by 9 is 2, so that's a yes. And you would just keep going through just like that. So for 11, this was my favorite one to work on. We have, you alternate the digits. So I'm going to pick a larger number to look at. So let's look at this one. So we would do 5 minus 0. Then we'd alternate to plus. So plus 2. Alternating back and forth, we have minus 5, plus 0, minus 5, plus 2, minus 8. That would give you, we have a negative 9 divided by 11. So that's not divisible. But if you look to this one, you have 6 minus 4 plus 4 minus 4 plus 9 minus 0 gives you 11. 11 divided by 11 is 1. So that was a yes. So that's a pretty cool trick. So let's move on to number 2. We're to use the process of nines to check each of the following answers. So that's casting out nines. So to solve these problems, we'll use the method of casting out nines. To do this, you add all the digits of each number together. If any of the numbers combine to get 9, like 6 and 3, you just cast them out or mark them off. Once you get those answers, you add them all again, casting out the nines. Finally, you take the given answer, add those digits, casting out nines, and if that number matches yours, then the answer is correct. On this problem, I feel like I've earned all the credit for it because I do enjoy casting out nines, and I think my work is correct. So here we were given 416 plus 7,490 plus 69,844, and the given answer we have is 112,790. So let's cast out our nines. So for 416, there is nothing to cast out because none of those add to get 9. So that would just be 11. 7,490, you cast out that 9, that gives you 11. This number, cast out the 9, you get 22. So then you'll cast out 9s again, add those together. So we have 2, 2, and 4, no casting out 9s there, and that gives us 8. For the answer, you're going to cast out 9, so 7 and 2 combine to give you 9, and then cross out 9, of course, and that gives you 2. So do 2 and 8 match? No. So the given answer was incorrect. The correct answer is 77,750. To add those together, you get 26. Add 6 and 2, you get 8. So 8 and 8 match. So you keep doing this for B. We find that their answer is incorrect because after you cast out the 9s, you were giving 6. We got 7. So the correct answer is 23,992 because both of those equal 7. You'll continue to cast out 9s for C and D, which is what we did, and we found that each answer was incorrect, and then we found the right one again by casting out 9s. So for number 3, the colored rods shown here are 1 centimeter square and the lengths 1 centimeter, 2 centimeter, 3 centimeter, so on to 10 centimeters. We say that a rod measures another rod if the number from the first rod placed end to end are the same length as the given rod. So we're to answer parts A through G. And my rods were colored until the paper was scanned, so I apologize for the darkness right here. Okay, so for A, we are to show which rods measure the 9 rods. So that would be 1, 3, and 9. 1 end to end, you would do 9 of those. 3 end to end, you would do 3 of those. 3 times 3 is 9. And 9, of course, pressed against a 9 rod would measure it perfectly. So which rods will measure the 6 rod? We have 1, 2, 3, and 6. 2 times 3 is 6. 3 times 2 is 6, and so on. And using visuals to do multiplication is probably one of the best things to do, because you'll see, like if you were to try to put an 8 rod and an 8 rod, obviously that's longer than a 6 rod and so on. So for C, use parts A and B to show the greatest common divisor of 9 and 6. So what that's asking is, what's the largest number that we were given that divides both 9 and 6 evenly? So is 1 the largest number? No, because if you notice, both of these have 3. That's the largest. So the GCD, or greatest common divisor, would be 3. For D, we're to place the 10 rod and the 8 rod end to end to form an 18 train. Show all the rods or trains that will measure the 18 train. We would have 1, 2, 3, 6, 9, and 18. So for E, it's asking us basically the same question. And again, our answer is 1, 2, 3, 6, 9, and 18. So for F, we are to briefly describe how you would use these rods to demonstrate the notion of the greatest common divisor to children. So like in C, I said the greatest common divisor is the largest number to divide those into. So I would give a problem like problem C listed before. It lets you use visuals to see how many times a number can go into a larger one, and it shows you that 3 is obviously the greatest common divisor for the above question. So to solve these problems, we were given a visual of rods. By seeing the problem this way, you're better able to understand it. When C asks for the GCD, all you have to do is look back at A and B to see what the number divides both 6 and 9 evenly, and the largest 3 was the answer. Combining the rods just adds to your answer possibilities. So I feel that I've earned all points for this problem. So for number 4, we have the LCM method demonstrated in the table as follows. Factor out the prime divisor, or one or more terms. Replace each term containing the prime factor by its quotient. We're to do this from A through C. So what we have here is our table. Our LCMs given are 48, 25, and 65. So those are written right here. So we're going to see what prime number can break these down. So we notice that 2 can break down 48. So we'll start with 2. So we write a 2 here. Divide by 2 if you can. If not, bring down the number. So this is 24, stays the same, stays the same. Again, until you can't do 2 anymore, you just keep writing it down until we finally come to our simplest form of 3. So then we get into what can break these down. They both end in 5, so 5, because 5 is a prime. So 3 can't break down by 5, and the rest can. So we have 3, 5, and 13. So now we're going to add these up. You see we have 4 2s, so that's 2 to the 4th. Times 5 to the 2nd power, because we have 2 5s, 3 to the 1st power, and then 13 to the 1st power. And that's just our breakdown. Okay, so we do the same thing for B and come out with 2 to the 3rd power, 3 to the 2nd power, 11 to the 3rd power, and 5 to the 1st power. For C, much the same. We are given 4 of these numbers of the LCMs, and then we're to break that down. So we go all the way down. We end up with 5 cubed times 2 squared times 7 times 11 squared. So at first glance, these problems can seem hard, but the table simplifies them for you. The LCM is the least common multiple. To find the least common multiple in prime power form, you place your LCMs in the individual spots and use prime numbers to simplify them. You start with the first number and work over until all numbers are simplified. You then count how many times a prime number appears on the outer side and place them in power form. Okay, so I felt like that problem, I deserve all points. So number 5, in a machine, a gear with 48 teeth is engaged with a gear with 84 teeth, with teeth A and B on the small and large gears respectively in contact as shown. How many more revolutions will a smaller gear have to take before A and B again are in the same position? So to solve this problem, we must find the LCM of 48 and 84. So we write the prime factorization of both numbers to find this. The prime factorization, let's see. Okay. So we then take the LCM and divide it by the number of teeth in the small gear, which is 48. This problem is easily solved using a factor tree to find the prime factorization. So down here, I talked about what the prime factorization is. So down here, 48 would come out to 2 to the 4th power times 3. 84 would be 2 to the 2nd power times 3 times 7. So then we just take that and we find the LCM, which is going to be 336. We're going to take 336 and divide that by the one with the smaller teeth, which is 48, and we come up with 7. So the gears are going to make 7 revolutions. Okay, so finally for number 6, we're going to use a magic square using the integers -7, -6, -5, -4, -3, -2, -1, 0, and 1. So all a magic square is a square in which all rows and columns have the same sum. first, you must find the magic number. What you're going to do is you're going to add all the integers, and on this problem, you get negative 27. Since there are 3 rows and 3 columns, you would divide the negative 27 by 3 to get a negative 9. You then place all the numbers so that negative 9 is the sum up and down. And so I feel that I've earned all points to this problem. So we'll see that we had to place 0 here, negative 2, negative 7, negative 4, negative 6, 1, negative 5, negative 1, negative 3. Now we were given 0 and 1 and they're given spots, and then we had to find everything else to give us negative 9. So all of those across and down equal negative 9. So my name is Alyssa Pierce, and I hope you learned a little bit more. And this was Module 3 exam. Thank you for watching. See you next time.